Welcome aboard the most innovative, powerful, and safe spacecraft, Chrysalis, which will take you to exoplanet Proxima Centauri B of the Alpha Centauri star system. Thousands of brilliant minds have been working for decades to provide you with a comfortable journey through the depths of boundless space. You won't live to reach your destination, as the entire way takes more than 400 years. But rest assured, your descendants will reach Proxima Centauri B completely healthy. Now let me give you a tour of the ship and show you how it works. To ensure that living conditions on Chrysalis are as close as possible to those on Earth, scientists equipped the ship with artificial gravity support. Thanks to the rotating hulls, you'll be able to walk here as if you're on your home planet. And the ship's length? A whopping 36 miles. Will definitely ensure you take long walks. You can sit on a bench in the park where botanists have planted flowers and trees grown on board. You can visit a library or have lunch at a cafe. You can meet your friends in the evening, or you can spend time at home watching documentaries about wildlife. Maintaining an earthly standard of living on the ship is possible thanks to the operation of thermonuclear reactors and the unique design of Chrysalis. The whole ship is built like a nesting doll. Several layers of the ship cover one another and spin around the central core. Each layer is equipped with a fusion reactor and public spaces, farms, warehouses, natural parks, technical departments, and many other facilities. The center of the ship has communication equipment and shuttles that will take you to Proxima Centauri B after Chrysalis approaches the upper layers of the planet's atmosphere. Factories for the production of food, plants, mushrooms, insects, microbes, and livestock are located on the level closest to the core. Earth's biodiversity is traveling with you to the neighboring star system. In order to maintain this biodiversity in natural conditions, engineers have equipped the ship with tropical and boreal forests. Scientists recommend regular visits to these natural areas to reduce anxiety and homesickness. The second level is designed to support passengers' social life. There are parks, schools, libraries, and hospitals here. Community and spending time together should protect you from existential horror and distract you from realizing how far away you are from your home planet. The next level of Chrysalis has an air and heat circulation center. If the core is the heart of the ship, then this area is its lungs. Then there's a layer designed for waste recycling, construction, and numerous factories. There will always be something to do on the ship, and you will never be out of work. This means you will never face a financial crisis. The last and furthest level from the core works as a giant warehouse for storing various resources, materials, equipment, and machines. In order not to burden people with additional work at this layer, engineers placed robots with artificial intelligence here. The ship's complex and multi-layered systems work to provide the passengers with the feeling that they're on Earth. But if you want to remind yourself where you really are, you can go to the front part of Chrysalis, where engineers installed a so-called space dome with a gravity zone. Here you will have a great time with zero gravity, enjoying an incredible panoramic view of space. In order to maintain a stable demographic and not provoke overpopulation of the ship, it's necessary to have at least 1,500 people on board. That's 900 people fewer than the stated capacity. Engineers and pilots responsible for managing the spacecraft will be cooperating with artificial intelligence. But of course, no comfort makes sense without security. The Chrysalis body has a cylindrical shape with a narrow front, which reduces the risk of impacts from small meteorites and space debris. Mobility, speed, and long flight time are provided by an engine working on a nuclear fusion isotope of helium and deuterium. It gives the ship a simultaneous boost of thrust and electrical power. Now, all your attention should be focused on the preservation of the human species. Over the course of 400 years, while the ship travels to its destination, several generations will change. Your kids and future descendants won't get the experience of living on Earth. Skilled teachers, engineers, and other professionals, along with artificial intelligence, will teach the next generation science, culture, and all the necessary knowledge that will help build our civilization in a new home. The success of the mission also depends on the psychological state of the passengers. For this reason, not everyone will be able to access the Cresselis board. To adapt the human brain to the conditions of terrestrial isolation, the first generations will need to spend approximately 70 to 80 years in a remote area of Antarctica. Obviously, after such a long period, many won't be alive anymore, but they will make their descendants ready for a space mission. The first generation will never see space and will spend their entire lives in the cold Antarctica. What kind of person can be prepared for this? Their renunciation of the world and sacrifice for the sake of other people will set an example of the highest manifestation of love. This fact adds more responsibility to your mission. You've just watched the presentation of the Chrysalis project, which won first place at the Project Hyperion Design competition. A group of specialists has prepared a well-thought-out plan to create a spacecraft capable of taking us to the nearest planet suitable for habitation. According to estimates, this ship can be built in 20 to 25 years. But first, people need to invent fusion reactors. This project is a practical instruction on how to start the expansion of space, or how it can work like Plan B in case a global catastrophe happens on our planet. But what is this planet that has captured the minds of scientists and astronomers? Could it potentially become our new home? Proxima Centauri B is located 4.24 light-years away. It's not easy for the human mind to imagine and realize this distance, but relative to the entire outer space, it's very close to Earth. 1 light-year is the distance that you travel during 1 year moving at the speed of light, which is approximately 983 billion feet per second. The distance Cresselis would have to cover is about 25 trillion miles, and the time needed for this journey is about 400 years. The ship would accelerate during the first year of this long voyage, and it'd slow down for the last year of the trip. It'd be a long, risky, and very exciting journey, but the result would be worth it. Proxima Centauri B was discovered in 2016. Its mass is 1.1 times that of Earth, and it orbits its star every 11 days. The distance between the planet and its star is ideal for getting enough light and maintaining temperatures above the freezing point of water. But because of this proximity, there is a possibility that Proxima Centauri B is under a strong influence of gravity and orbits the star with one side, like the Moon orbits Earth. Anyway, the planet immediately attracted everyone's attention because it turned out to be very similar to Earth in many ways. Scientists used special computer models to study Proxima Centauri B. The same models are used to study the climate of our planet. They found out there might be huge areas of liquid water in that distant world, and probably living organisms. But if the planet is always facing the sun with one side, there's probably a huge temperature imbalance. Fortunately, this problem can be solved. According to new calculations, Proxima Centauri B might have a large circulating ocean that can effectively transfer heat from one side of the exoplanet to the other. A similar process happens on Earth. For example, the east coast of the United States has a milder and warmer climate because the Gulf Stream carries warm water from the tropics there. In California, the ocean current brings cold waters from the north and prevents this side from getting too hot. So maybe Proxima Centauri B is really not a bad option for us.
Whoa! A wall of fire spreads around the epicenter of the impact. It burns everything in its path. The waves raised by the explosion cover large cities, and earthquakes are so strong that giant skyscrapers fall like a house of cards. So, these are the possible consequences of the collision with the first interstellar object in history to visit our solar system. We discovered it in 2017, but we're still not sure what it is: an asteroid, a comet, or a spaceship of some outer space civilization. So far, scientists have named it Oumuamua. Sounds like a Hawaiian cow. Well, whatever it is, its speed is much faster than other asteroids. about 54 miles per second. At that speed, you could cross the US from coast to coast in less than 3 minutes. So this asteroid could travel from Earth to the Sun in about 2 months. By comparison, our rockets can travel up to 17,000 miles per hour. The same trip across the United States would take them about 9 minutes. So many scientists speculate that this is an artificial object created by a very advanced civilization. Okay. The shape of the object supports this theory. It's long and narrow and resembles a spaceship. It's about half a mile long, way bigger than the Eiffel Tower. Scientists decided to see if Oumuamua was really someone's spaceship and pointed some radio telescopes at it. If the civilization on that ship had used communication or scanned us with their tech, we would have known about it. But there was complete silence. Kind of like that. Not a single radio wave. But that doesn't disprove the theory of outer space civilization. To find out for sure, we decided to determine the weight of the object. To do that, we use light. More precisely, its reflection. You see, different materials reflect light differently. We take an unknown black stone, for example. It absorbs almost all the light, reflecting almost nothing. Check out the catalog, it's charcoal. Knowing the size and material of the object, we can determine its weight. So, we need to see how much light this object reflects. And when scientists pointed their telescopes at Oumuamua, they learned that it reflects colors that match with iron and also with some solid rocks. And Oumuamua was flashing all the time, a bright flash. Then it would slowly fade, and then it would start to shine again. This means it was spinning. And it wasn't going around its axis like an arrow. It rotated chaotically, moving its edges up and down. Any artificial object or spacecraft would have been torn apart by such overloads. But Oumuamua is still intact. That means it's made of super hard materials that keep it from falling apart. And it's not hollow like a spaceship. It's one solid body. Hey, like me. The astounding speed of this object makes it pretty mysterious. Some comets can have the same or even higher speed, but they also have a kind of rocket effect. So when a spaceship starts from the launch pad, you see fire bursting out of its engines. Every second, the rocket mixes fuel with oxygen, ignites them, and ejects them at a tremendous speed. According to the laws of physics, this is like pushing off a wall. The rocket sort of jumps up from the combustion gases it throws down. That's how the rocket creates thrust and accelerates. Comets work on a similar principle. The sun's rays hit the surface of the comet. Light elements like ice start to evaporate. That gas goes one way, the comet goes the other. Just like a rocket, the comet is pushing off the evaporating gas and accelerates. This gas also forms the comet's long tail. It's as if the massive rock is dragging all this gas behind it. I can relate. Or it's like a car pulls air with it when it goes at high speed. But Oumuamua is not a comet, and it doesn't have that tail, and it doesn't have the same rocket effect as a comet. So it couldn't have accelerated to that speed. But some scientists believe that Oumuamua used to have a tail. Although we discovered it in 2017, it entered our solar system in 1995, and it was hit by the sun's rays even back then. When we discovered this asteroid, it had already lost about 95% of its mass. It simply evaporated. Other scientists believe that Oumuamua got this velocity during its birth, somewhere far away in another star system or nebula. Perhaps it was a dramatic collision of some exoplanet with another cosmic object. The colossal explosive energy of the collision threw the elongated shard into outer space. Or it could have been a supernova explosion. When a star reaches the end of its lifespan, it becomes a red giant. It's an inflated version of the star, hundreds of times bigger. Then it shrinks and explodes with tremendous force. The blast waves can travel many light years away from the epicenter, and it's one of the brightest events in the universe. So the supernova might have torn some exoplanet to pieces. One of them, Oumuamua, gained a lot of energy and speed and began its long journey toward Earth. This might explain why Oumuamua keeps spinning so wildly. But recently, scientists published a theory that Oumuamua may be a giant block of ice. The kind of ice we're used to is water, H2O, but Oumuamua could be nitrogen ice, N2. It may have remained intact in interstellar space for 500 million years. And when it arrived in our solar system, nitrogen ice could have reflected 2/3 of the sun's rays, so it didn't heat up as much. That explains why Oumuamua doesn't have a tail. You can find the same nitrogen ice on Pluto, as well as on Triton, one of Neptune's moons. So Oumuamua comes from a similar icy exoplanet. But we can find out for sure only by sending a space probe to it. Scientists came up with a plan for that called Project Lyra. The problem is that Oumuamua is leaving our solar system at tremendous speeds, much faster than our rockets can fly. And we need to catch up with this space rock as quickly as possible before it gets too far away. To do this, we can use a gravity maneuver. First, the space probe makes a flyby of Jupiter. It passes close to it to take advantage of its gravity to accelerate. After that, the probe will head towards the Sun, and it'll fly around it as close as possible to fire like a catapult towards the space rock. The second option for reaching the asteroid is to use microprobes. We have to launch about 1,000 of them into orbit. They should be no heavier than a match. Each of them will have a light sail the size of a boxing ring. Then we'll focus a powerful laser beam from the ground onto this sail. It will allow us to accelerate the probe to about 20% of the speed of light. It shouldn't go too fast not to fly past the asteroid. It should be able to enter its orbit or land on it. But if we're too slow, Oumuamua will leave our solar system before we can catch up with it. It'll be a great experience because in the future, we'll be able to use such asteroids as a space taxi. All we have to do is enter the orbit of such an interstellar asteroid or even land on it. Then we would keep moving through space at incredible speeds without using any fuel at all. This would be a great option for traveling long distances or to deliver supplies to other star systems. So why should we be afraid of such objects? Well, a collision with an asteroid the size of Oumuamua could wipe out an entire state. If it were to hit somewhere in the ocean, it could cause waves taller than our skyscrapers. Scientists are anxious to find ways to protect us against such objects. One of them is ramming. If we spot a potentially hazardous object, we could send a spaceship towards it, pedal to the metal. The spacecraft will have to ram the asteroid at an angle that will move its trajectory just a little bit. Moving it too much on a cosmic scale would only dramatically change the asteroid's final destination, and we only need to get the asteroid past our planet. We can also create a controlled explosion on the asteroid. It's based on the same principle. The force of the explosion would have to shift the trajectory of the asteroid slightly, or smash a giant rock into smaller pieces. Asteroids up to 80 feet wide would burn up completely in our atmosphere due to friction against the air. Rocks between 80 feet and half a mile in size may not burn up completely and cause local damage. Anything larger is considered very hazardous. You think? The traditional method of science fiction is to put rocket engines on the asteroid. Then we can not only change the trajectory of the space rock, but also control it. And we can use it against other asteroids. It would be something like space billiards. A recent shocking discovery, shocking I tell you, shows that one galaxy can devour another smaller one, leaving behind just faint remains. Can anything like this happen to our home Milky Way galaxy? And if it does, what will happen to the inhabitants of the planet Earth? You know, us. Well, let's figure it out. This whole discovery is actually a curious story. Even before the Rubin Observatory, an astronomical observatory in Chile, even started its full science work, it accidentally helped astronomers spot something totally unexpected. In June, the team released its very first test images, and one of them showed a deep look at the Virgo cluster. That's a huge group of nearby galaxies scientists have been studying for years. But in the bottom right corner of that image, there was something thin and strange, and it wasn't me. It was a tiny razor-sharp streak of stars stretching away from a well-known galaxy called M61. No one had ever seen it before. Now, M61 looks a lot like our own Milky Way galaxy. It's a barred spiral galaxy with long, sweeping arms. But despite the similar shape, the center of M61 is far more dramatic. While Milky Way's supermassive black hole sits quietly, almost as if it's asleep, M61's black hole is wide awake and hungry. It feeds on surrounding matter and blasts out powerful flows of energy, which creates a kind of galactic storm that spreads through the galaxy. M61 has been studied for decades, but Rubin's camera is built to pick up things that are extremely faint. That's why this new star system suddenly appeared. It was as if someone turned on a flashlight in a dark room. Now, the stream is enormous. It's about 50 kiloparsecs long, which is roughly 163,000 light-years. That's more than the size of the entire Milky Way. Most stellar streams around our own galaxy are only a few tens of thousands of light-years long, so this one is huge by comparison. Scientists think that the long trail is made of a dwarf galaxy that got too close to M61. Once it crossed into the larger galaxy's territory, the dwarf galaxy became trapped in its gravitational grip. Little by little, powerful tidal forces began pulling it apart, stretching it into a long, faint trail of stars. Eventually, it was completely ripped apart by M61's gravity. When that happened, the larger galaxy seemed to have responded with a burst of new star-making about 10 million years ago. It almost felt like the collision kicked it awake. This process, large galaxies tearing smaller ones apart, is thought to be one of the main ways galaxies, like the Milky Way and M61, grow over billions of years. Each smaller galaxy that falls in becomes fuel for the larger one, adding stars and gas, and sometimes this process can even stir up activity around the central black hole. Will our Milky Way become that smaller galaxy one day? Well, we do have a much bigger neighbor, the Andromeda Galaxy. But at the moment, we can't predict whether it'll get hungry enough to attack the Milky Way. Whew, what a relief. Anyway, it might seem weird that the M61 stream had gone unnoticed for so long. It wasn't exactly faint or subtle, glowing with the light of about 100 million suns. Hard to miss. But it managed this trick by staying hidden behind a nearby galaxy. This makes it really difficult to detect even bright stellar streams. To find them, we need extremely sensitive instruments and careful techniques. At least now we know that giant galaxies may grow by eating smaller ones, leaving long trails of stars behind as evidence. The researchers admit that it's surprising that such a huge structure stayed hidden around a famous galaxy for so long. And it seems that the discovery of the M61 stream is just the beginning. The night sky might start filling with new uncovered structures, ghostly trails, forgotten galaxies, and the remains of ancient cosmic encounters. The Rubin Observatory is a brand new astronomy center built on a mountain in Chile. Its full name is the Vera C. Rubin Observatory. It was named after the astronomer who first found strong evidence that dark matter is real. Now, what makes Rubin special is that it's the first telescope of its kind. Its giant mirrors, super-sensitive camera, fast movement, and powerful computers all use cutting-edge technology. The main telescope, called the Simonyi Survey Telescope, has a 27-foot mirror, and it uses the LSST camera, which is the biggest digital camera ever made. But we'll talk about it a bit later. For 10 years, this telescope will take extremely detailed pictures of the southern sky. It will scan the entire sky every few nights, creating a huge, high-quality time-lapse video, the largest movie of the universe ever recorded. This movie will help scientists spot things that change over time, like asteroids, comets, stars that get brighter or dimmer, and exploding stars called supernovae. To create this giant time-lapse, the Rubin Observatory will have to use a lot of new technology. Some of its parts were invented from scratch, and others were improved versions of older designs. It'll help scientists discover all kinds of things. Many we already expect, and many we can't even imagine yet. Even so, Rubin Observatory was built with 4 main science goals in mind: learning more about dark matter and dark energy, creating a complete list of objects in our solar system, mapping the structure of the Milky Way, and studying objects that move or change brightness over time. Everything about the telescope, its huge size, fast scanning speed, and ultra-sensitive camera, was designed to make discoveries in these 4 areas as complete as possible. Rubin's telescope isn't the first telescope with a mirror about 27 feet wide. but it is the first to combine its primary mirror and tertiary mirror into one single surface. Putting both mirrors together is a special innovation that makes the entire telescope more compact. Because of this, it can move faster and get ready for its next observation much more quickly. The telescope's LSST camera is the biggest digital camera ever created. It's about the size of an SUV and weighs around 6,000 pounds. It holds a giant 3,200 megapixel CCD array. Just one single picture from Rubin is so large that you'd need about 400 Ultra HD TV screens to display it. It's also the fastest-moving large telescope on Earth. Rubin's telescope can swing into a new position in only 5 seconds and immediately start taking its next image. The speed comes from the telescope's compact design, thanks to its 2-in-1 mirror and its powerful drive motors. They can quickly move and stop the 220-ton telescope mount without shaking it. Even small vibrations can ruin an image, so this stability is a huge achievement. By the way, if the telescope were spinning at full speed, you wouldn't be able to outrun it. Also, Rubin Observatory has a rare combination. It can collect a lot of light and capture a very large area of the sky in a single picture. This means it can spot faint objects spread out over a wide region without needing many separate images. When you add the telescope's incredible speed, you get the perfect setup for creating Rubin's ultra-high-definition 10-year time-lapse of the universe. A fun fact, each Rubin image covers about 10 square degrees of sky. That's the same area as 45 full moons, or about the size of a golf ball held at arm's length. Another cool thing is that Rubin data will be immediately available to scientists in the US and Chile, and to members of Rubin's International In-Kind program. They'll be able to access everything through an online portal, which means that no giant downloads are needed. After 2 years, the entire world will be able to view Rubin data. Rubin will also process new images every night in near real time. If something in the sky moves or changes, the system will send out a public alert within 60 seconds. This will allow scientists to respond quickly and point their telescopes at the event. Each night, Rubin Observatory will create 20 terabytes of data and send out up to 10 million alerts about changes in the sky. By the end of the 10-year survey, Rubin will have produced a whopping 60 petabytes of raw images. It'll be the first time so much astronomical information is shared with so many people.
An ultra-powerful explosion happened just outside the Milky Way galaxy, kinda next door in cosmic terms, and it was unlike anything we've witnessed before. The thing kept blasting again and again, shooting out crazy strong bursts of energy called gamma rays. It was almost an entire day of non-stop firing back in July 2025. In gamma ray time, that's basically forever, because normally gamma ray bursts last from a few milliseconds to a few minutes, not hours on end. But the craziest thing is that this phenomenon might be linked to an elusive and mysterious kind of black hole, the existence of which we haven't proven yet. Scientists gave this phenomenon a complex sciencey name. Usually, these gamma ray bursts happen when a giant star goes off. One big dramatic exit, and that's it. But this space diva didn't get the memo and kept coming back for encores. NASA's Fermi telescope first spotted this bizarre space performance on July 2nd. But then some other space gear, the Einstein probe, realized it had already been blasting the day before. Scientists tossed around a few guesses. It could have been a massive star, like 40 times the size of our Sun, that went out in a special kind of way. Not your average star demise, but one that somehow kept its cosmic engine running, like a car that won't stop even after the gas runs out. Another theory is even wilder. Some scientists think those space fireworks might have gone off when a star, likely a tiny one called a white dwarf, got shredded by a black hole. It's like a cosmic blender moment. They call it a tidal disruption event, or TDE. You see, not every star goes out with a giant boom like in the movies. Most just get old, puff up, and slowly fade away, leaving behind their tired little cores. Those leftovers are called white dwarfs, star corpses made of super weird squished up gas. You see, what happens to a star when it goes off depends on how big it was when it was born. Stars that start out kind of small, about the same size as the Sun or up to 10 times bigger, usually end up as white dwarfs. Most of the time, these stars run out of fuel and blow off their outer layers, creating a glowing cloud called a planetary nebula. What's left behind is the super hot dense core, about the size of Earth. That's the white dwarf. They're still really hot when they form and slowly cool down over time. After billions of years, they might turn into cold, dark, black dwarfs. But the universe isn't old enough for any of those to exist yet. Anyway, let's get back to our investigation. If this second theory is right, the black hole responsible for this cosmic show wasn't a regular one. To pull off something like this, it would need to be a super rare kind of black hole. One of those mysterious intermediate mass black holes scientists have been trying to find forever. Before we move further, let's take a look at the black hole lineup. Small ones are called stellar mass black holes. They're formed when massive stars weighing somewhere between 20 to 100 suns collapse. Supermassive black holes are real space behemoths. They're millions and even billions of times heavier than the Sun. They chill at the centers of galaxies. Even our home Milky Way galaxy has one called Sagittarius A star. This black hole is mostly dormant. It absorbs gas or dust only occasionally, but its estimated mass is millions of times that of our Sun. There might be one more type of black hole: primordial black holes. Scientists think they might have formed in the very first moments after the birth of the universe. That's when pockets of hot material could be dense enough to form black holes. Their masses might have ranged from 100,000 times less than a paperclip to 100,000 times more than that of the Sun. After that, the universe expanded and cooled very fast, and the conditions for forming black holes this way came to an end. These days, 13.8 billion years later, astronomers still haven't found definitive proof that those primordial black holes even existed. On the other hand, it's possible that they could have evaporated as space became older, due to certain processes happening at the edges of their event horizons, aka the points of no return. According to theoretical predictions, lower mass black holes with less mass than a mountain could evaporate more quickly than larger ones. If this idea is correct, then many of those early black holes have already completely dissipated. But more massive primordial black holes could still be lingering across the universe. Anyway, if we get back to the already proven kinds of black holes, between stellar-sized black holes and supermassive ones, there are elusive intermediate mass black holes. Scientists think they exist, but they're like Bigfoot. Lots of theories, not much proof. Astronomers think that small black holes might crash into each other and merge over time to form those medium ones, but spotting one is almost impossible. They're sneaky and silent. People often tend to mistake them for star graveyards, clusters of smaller black holes just hanging out. Sometimes, intermediate mass black holes even hide behind groups of stars that orbit them real close. The best way to catch such a black hole is to look for clues. Scientists measure the mass of black holes when they crash into each other, or spot them mid-meal when they're munching on a nearby star. So far, around 300 possible intermediate mass black holes have been found, but no one is totally sure which ones are the real deal. And now, astronomers think they've finally caught this super rare missing link black hole. Right now, it might be snacking on a poor star way out at the edge of some distant galaxy. In a study published on April 11, 2025, scientists talk about a black hole called HLX-1. It's hanging out about 40,000 light-years from the center of its galaxy and roughly 450 million light-years away from us. Using data from NASA's Hubble Space Telescope and the Chandra X-ray Observatory, the team spotted a bright flash, that very tidal disruption event that occurs when a black hole tears a nearby star to pieces. Then they ran computer simulations to recreate the whole thing, and it showed HLX-1 stretching the poor star like space spaghetti. By the way, this process is indeed called spaghettification. Astronomers have their own cosmic jokes, you know? Anyway, scientists first spotted something weird going on with HLX-1 back in 2009. NASA's Chandra X-ray Observatory caught a super bright glow coming from deep space. Turns out, it could have been another tidal disruption event. The glow from HLX-1 hits its peak around 2012, and it's been fading ever since. But of course, there's a catch. Nobody's totally sure it's a real intermediate mass black hole. You see, that light might not be from a shredded star at all. It could be from an accretion disk, a giant, super hot ring of gas and dust swirling around the black hole's edges. And the only way to figure out what's really going on is to keep watching. If the light keeps fading and doesn't flare back up, then yeah, that poor star probably got eaten. Intermediate mass black holes are a big deal because they're the missing link in the black hole family tree. The connect the dots piece in understanding how black holes grow up. There's also an idea that intermediate mass black holes might start out as big stellar mass black holes and just keep bulking up over billions of years until they become those massive, city-sized monsters at galaxy centers. That means most of their lives, they're probably lurking way out on the galaxy's edge. Like HLX-1, before they get launched into deep space. And now, some scientists think there could be a sneaky intermediate mass black hole hanging out on the outskirts of our Milky Way right at this moment. Even if there isn't, the research team is still keeping an eye on what's happening after that blast and trying to piece together what in the universe actually caused it. Next up on their to-do list is figuring out exactly where it happened. Once they pin down the location, they'll be able to measure just how much cosmic energy this thing pumped out and how big the explosion really was. At breakneck speed, this mysterious object is zipping through our galaxy. It's moving at a staggering 1 million miles per hour. That's so fast it might potentially escape the Milky Way altogether. While scientists are trying to understand exactly what this space weirdo is, we're going into space to learn more about it. The object is currently moving at a distance of 400 light-years away from Earth. Let's have a closer look and try to figure out if it could be a runaway probe. Nah, it's way too large for that. The object is around 30,000 times the mass of Earth and 8% of the mass of the Sun. What a giant! Such a size places it in a category that Dr. Darren Baskill, an astronomy lecturer at the University of Sussex, describes as somewhere between a star and a planet. Stars moving at such extreme speeds are super rare. Only 1 or 2 out of every 1,000 local stars travel so incredibly fast. So, if one day you found a star moving as rapidly as our cosmic enigma, you'd see it leave our home Milky Way galaxy in just a few tens of millions of years. In terms of space and cosmic distances, it's a blink of an eye period of time. After all, such stars can live for tens of billions of years. Even though the mysterious object is only moving at 0.001% of the speed of light, it's still potentially fast enough to eventually break free from the gravitational pull of our galaxy and fly into intergalactic space. Let's put this speed into perspective. J1249 is traveling 2.6 times faster than the fastest space probe ever launched. I'm talking about the Parker Solar Probe. The Parker probe reached this speed in June 2024 while looping around the Sun. J1249 was discovered by citizen scientists volunteering for NASA's Backyard Worlds Planet 9 project. These volunteers sift through online images taken by NASA's Wide Field Infrared Explorer and NEOWISE missions. They're looking for anything interesting. 3 of those volunteers spotted a faint, fast-moving object as it moved across WISE images. When they realized what they were looking at, they were incredibly excited, but thought someone had already reported the space object. But surprisingly, that wasn't the case. At the moment, most scientists believe that CWISE J1249 could either be a low-mass star or a brown dwarf. That's a type of star that is larger than a planet but too small to support nuclear fusion in its core, like our Sun does. In other words, such stars don't have enough mass, and their cores can't burn their star fuel, radiating starlight. That's why brown dwarfs, often referred to as failed stars, are smaller and cooler than the Sun. They even have complex planet-like atmospheres, which have clouds and molecules. For example, H2O. Anyway, to confirm or disprove this theory, astronomers continued to observe the object with the help of ground-based telescopes. Soon, they found out that the object had an unusual composition, with much less iron and other metals, compared to typical stars or brown dwarfs. It allowed NASA to claim the unthinkable. J1249 could be one of the oldest stars ever found in our galaxy. Okay, that's certainly a game changer, but why is this potential star moving so fast? The research team has a few theories. For example, the object might be the remains of a binary star system where its companion, a white dwarf, exploded in a supernova after pulling too much material from J1249. Another possibility is that our mysterious traveler may have originated from a cluster of stars that dispersed after coming across two black holes. According to experts, one way to get to such extreme speeds is to fall toward an object and miss it. Such gravitational slingshots are how space probes are accelerated to extreme speeds, which allows us to explore the solar system up close over reasonable timescales. The same technique could also explain the speed of J1249. The star could have been born in the crowded center of our galaxy. Then it might have fallen toward a star, missed, and in the process was accelerated to extreme speeds. Well, let's leave astronomers to search for more evidence to confirm this exciting theory. Meanwhile, we're heading further to the binary star system 55 Cancri. It lies 41 light-years away from Earth and hosts an amazing planet, 55 Cancri E, also known as Janssen. This is a scorched super-Earth, 8 times the mass of our planet, and it orbits its star in just over 17 hours. Yep, the year on this planet is shorter than 1 day on Earth. Plus, it's 25 times closer to its star than Mercury is to our Sun. No wonder the planet's surface reaches blistering temperatures of 4,350 degrees Fahrenheit. That's hot enough to melt nearly any known metal. Back in 2010, a study found out that the host star of 55 Cancri E had an unusually high carbon-to-oxygen ratio. If this ratio was also true for the planet, it would mean that 55 Cancri E might have huge quantities of carbon. And the coolest thing? It would be in the form of diamonds. It'd make this space body a literal diamond planet. Sadly, some follow-up studies discovered that the carbon-to-oxygen ratio on the planet was less extreme than originally thought. It makes the idea of a diamond-encrusted world less feasible. On the bright side, planets don't always have to match the composition of their host stars exactly. If some other process topped up the carbon on 55 Cancri E, it could still be the most precious planet known in the universe. Definitely worth a visit. But let's leave the diamond planet behind and fly to Vega, which holds a special place as one of the brightest and most important stars in the sky. The brightest of other stars is measured against the brightness of Vega on a special magnitude scale, where Vega's magnitude is 0. A star with a magnitude of 1 is 2.5 times dimmer than Vega, and a star with a magnitude of -1 is 2.5 times brighter. Vega is also a pole star, although not at the moment. Right now, Earth's axis points toward Polaris, the North Star, but Earth's axial tilt draws a circle over 26,000 years, and Vega will again be the pole star in about 12,000 years. Just you wait. But the coolest thing about Vega, which sets it aside from other stars, is that it's not shaped like a perfect sphere. Unlike the Sun, which rotates slowly and is almost spherical, Vega spins very fast, completing one rotation in just 12.5 hours. And it causes it to bulge at the equator, taking on an egg-shaped appearance. And now, get ready for the most dangerous encounter of them all. But first, I must warn you. Even though space is unimaginably vast, it's populated extremely sparsely. The universe's average density is equivalent to 6 protons in 35 cubic feet. But some areas, known as voids or supervoids, contain even less matter. These regions are enormous and can span 30 to 300 million light-years, and there's almost nothing there. There are also places in the universe where time and space are distorted in ways that challenge our human comprehension, like binary black hole systems, where 2 massive black holes dance around each other before eventually merging. As they spiral closer, they release immense gravitational waves that ripple across space-time. The first detection of such waves was made by the Laser Interferometer Gravitational Wave Observatory in 2015, when it recorded the final collision of a black hole pair. In the final 20 milliseconds before the merger, the black holes released more gravitational energy than the total energy emitted by all the stars in the observable universe during the same period. But that's not all the universe has to offer. Once you start exploring, you can come across exoplanets, like Corot 7b, where rock clouds form and send pebbles raining from the skies, or Kelt 9b, the hottest known planet with surface temperatures reaching 7,800 degrees Fahrenheit, or Tres 2b, the darkest planet ever discovered. It absorbs over 99% of the light it receives, making it blacker than coal. So, as you can see, in the vast, almost incomprehensible scale of the cosmos, mysterious, fast-moving objects, strange planets, and immense voids serve as a reminder of how much we have yet to learn about the universe. Is there a giant mega-sun in the center of our Milky Way? Scientists actually thought so for a while because it's the brightest place in the galaxy. It has millions of stars packed into a small area. This area is called the Gigantic Bulge. The Gigantic Bulge has millions more stars per light-year than any other part of the galaxy. It can be 10 million times denser than our part of the neighborhood. In some cases, stars in this region are only 5 light days apart. That's like if there was another star in our solar system a bit further away than Pluto on a space scale. But why is this place so dense? When galaxies form, a lot of gas and dust come together under the force of gravity. This material gathers up and eventually forms stars. Gravity and angular momentum balance out, and it starts looking like a flat disk with a pretty bright, bulging, dense core. The stars live their comfy lives, and once they get to the finishing line, they collapse under their own huge weight. Then, the black hole forms. Black holes love to eat everything around them, and the more they eat, the bigger they get. And what place is more perfect for a fine dinner than the galaxy's center, where all the space stuff is packed together? So it starts eating surrounding gas and dust, forming an accretion disk. As this material spirals into the black hole, it heats up and emits a lot of energy, which makes the center of the galaxy even brighter. That's why you can find both supermassive black holes and galactic bulges in the centers of all galaxies. The galactic bulge at the center of the Milky Way looks a bit like an ellipse. That's a classical bulge. Stars aren't like our sun. They move randomly in all possible directions and planes. Plus, they all move at different speeds. So gravity is going crazy there, and this makes the bulge look more like a sphere, or an ellipse. Since they were the first ones to form, they have some of the most ancient stars in our galaxy. But there are also some places of star formations and lots of younger, massive stars that are less than 100 million years old. As we move farther away from the center, things get a bit calmer. Stars start rotating uniformly and become stable. Right now, Earth is in one of the Milky Way's spiral arms called the Orion Arm, pretty far away from the galactic bulge. In our part of the neighborhood, stars are usually about 4 or 5 light years apart. This means that most of a galaxy is actually just black, empty space. Our black hole is called Sagittarius A star. It's a monster about 4 million times the mass of our Sun. It's also about 32 million miles in size, almost like the distance between Mercury and the Sun. But don't worry, it's not attracting the Milky Way inside it, and it's not gonna eat us. These black holes are actually super small compared to the entire galaxy, so they can only eat whatever's around. Right now, many stars orbit Sagittarius A star, and even though it emits a huge amount of energy, we can't see its light from Earth without a lot of scientific effort. But why don't we see the center itself? The galactic bulge is so bright that even though it's 26,000 light-years away, we should see it shining brightly in our sky. Yet we don't. Turns out it's all because of space dust. There's a lot of dust between us and the core, and it absorbs most of the visible light. We can only look at the galactic core using other types of light, like near-infrared, gamma ray, and so on. NASA has images of the core in different types of light, and it shows how scarily bright the center is without the dust blocking our view. But not all bright regions are blocked by gas and dust. For example, when we look at dense clusters like the Messier 13, the stars are so close together that they look just like a white spot. Most of our telescopes can't separate them from each other. The satellite galaxy M32, our neighbor near the Andromeda galaxy, has about 84 stars per light-year. It's so dense that stars can't be resolved even by the Hubble Space Telescope. To get the idea, our solar system is 2 light-years long. We'd see about 168 stars outside our window if we were there. Our closest star is Alpha Centauri. It's about 4 light-years away from the Sun. If it was just a couple of light days away, it would shine much brighter than the full moon. So if we somehow managed to survive in crazily dense star regions, the sky would be white all day long. But it's unlikely that we'd make it. As we get closer to the center of the Milky Way, the chances of finding life get super slim. The gravity of stars is going wild with chaotic movements, so there are barely any planets around. On those miracle planets, the radiation from cosmic rays is skyrocketing. Supernova blasts and star collisions nearby become an everyday occasion, and all the gas around makes it basically impossible to breathe or even see properly. At the same time, as we move further away, there are fewer stars around. Elements that are super useful for life, like carbon, oxygen, and iron, are produced by stars, so they also drop. Too much radiation is awful, but too low radiation means that there's not enough energy to support chemical reactions, like photosynthesis. Which is why, if there is extraterrestrial life, it would most likely be somewhere in the middle of different galaxies. But some galaxies get their brightness from a so-called active galactic nucleus. These are extremely energetic regions at the center of some galaxies. They shine much brighter than any stars imaginable, although it mostly shines only in certain parts of the electromagnetic spectrum. The brightness comes not from the stars, but from the accretion disk around their supermassive black holes. As the material slowly falls into a black hole, it gathers around it and creates this flat, spinning disk of gas, dust, and other stuff. Since the gravity and friction there are insane, this disk heats up and starts emitting enormous amounts of energy. Also, this disk spins incredibly fast, almost at the speed of light. Because of that, collisions there happen all the time, and they're unimaginably powerful. They release even bigger amounts of energy. Most galaxies don't have an AGN. Those that do, like the galaxy M87 in the Virgo constellation, are called active galaxies. There are also different types of AGNs: the Seyfert galaxies, radio galaxies, and finally, the winners of our space brightness competition, quasars. Imagine things so bright that they can outshine the entire galaxy they belong to. Quasars are a specific type of active galactic nucleus, the most extreme and luminous form. They belong to the supermassive black holes, the biggest ones in our universe. Quasars are like a combination of several things. First, they're the brightest accretion disks in our world. because of their behemoth black holes eating everything around. But they have some cool features. For example, they have powerful jets of particles that shoot out from the poles of the black hole at nearly the speed of light. These jets add up to the brightness of the quasar, although they can only be seen in radio wavelengths. The energy they emit is so intense that they can be seen billions of light years away. However, the nearest quasar to us is 600 million light years away, so we can't see them with backyard telescopes. So, when we look at a galaxy through a telescope, we usually see only the brighter core, not the outer parts. Unfortunately, our eyes just aren't made to see things like the active galactic nucleus. So, these stars are the brightest things we can see. But what a beautiful sight it is.
The Milky Way galaxy, where we live, looks like a ginormous pinwheel rotating in space. It's a spiral galaxy that appeared around 14 billion years ago. It's filled with a lot of stuff: stars, nebulae, which are clouds of dust and gas, planets, asteroids, you and me and your parents and that messy kid down the street. You get the idea. And all these fan out from the center of the galaxy in long spiraling arms. A marvelous view. The Milky Way is about 100,000 light-years across, and it takes our Sun, along with all the solar system, 250 million years to make one revolution around the center of our home galaxy. Wow, that's a big lap. Look at the sky at night, and most stars you see there would be located in just one of the Milky Way's arms. Before telescopes were invented, people couldn't see stars clearly. They blurred together into a single white streak stretching across the sky. It looked like a river of milk, and that's how the name of our galaxy appeared. Now, let's get down to some recent and very exciting news. An international team of scientists have discovered something they've never seen before, hidden in the center of the Milky Way. It resembles Morse code. Is that our galaxy trying to communicate with us? In the early 1980s, astronomers discovered giant one-dimensional filaments dangling vertically near Sagittarius A star. That's our galaxy's central supermassive black hole. And recently, a new kind of such filament has been found. But they're much shorter and lie either horizontally or radially. In other words, they're spreading out like spokes on a wheel, going away from the black hole. Interestingly, even though both types of filaments do have certain similarities, researchers believe they most likely have different origins. The vertical filaments stretch through the galaxy, towering up to 150 light-years high. But the horizontal ones resemble the dashes and dots of Morse code. Scientists were beyond excited when they made this discovery, but they had to do a lot of research to make sure the structures indeed were what they looked like. They managed to confirm that the filaments were not random, but tied to the outflow of the black hole. Thanks to them, it became possible to study the spin of the black hole and the orientation of its accretion disk, a rotating disk of matter formed around the black hole under the influence of its immense gravitational force. But let's have a closer look at the filaments we've been talking about. There are around 1,000 vertical ones. They appear in pairs and clusters and are often either equally spaced or side by side like strings on a harp. As for their horizontal counterparts, they seem to be around 6 million years old. Now, both types of filaments are one-dimensional. They can be viewed with radio waves, and they seem to be tied to processes happening in the galactic center. That's it. The similarities end there. The vertical filaments are perpendicular to the galactic plane. The horizontal ones are parallel, but at the same time, they point radially toward the center of the galaxy and the black hole. The vertical filaments are magnetic. The horizontal ones seem to emit thermal radiation. The vertical filaments contain particles moving at speeds very close to the speed of light. The horizontal ones don't do it. There are way more vertical filaments, and they're much larger than those stretching horizontally, 150 light-years against 5 to 10 light-years at most. In any case, the new discovery is still filled with tons of unknown things, and astronomers are ready to start unraveling them. But the filaments aren't the only unexpected and bizarre phenomenon in the solar system. Some time ago, Australian researchers discovered a weird spinning object in the Milky Way, and it was unlike anything they'd seen before. This object released massive bursts of radio energy 3 times every hour. And even though there are other objects that switch on and off, for example pulsars, such frequent pulsation has never been observed before. Some astronomers admitted that this discovery was pretty spooky, since no known object in the sky could do it. Research teams started working on the discovery and found out that the object is likely to be 4,000 light-years away from Earth. It's also super bright and has an incredibly strong magnetic field. And still, if you do all the math, not me, you'll discover that it isn't supposed to have enough power to produce such radio waves every 20 minutes. The theories about the origin of this mysterious object vary. Some experts claim it could be an ultra-long period magnetar, whatever that is. Others think it might be a white dwarf or the remnants of a collapsed star. But it also might be something we've never heard about, an entirely new type of object. But one thing is clear, astronomers managed to observe the signal across a wide range of frequencies, which means it has a natural origin and isn't something artificial. Now, there's another mystery about the Milky Way. Hey, what can I say? It's a mysterious place. Around 15 years ago, astronomers launched the Fermi Gamma Ray Space Telescope. Gamma rays are an incredibly high-energy form of light. That's why, when you observe the sky through the gamma ray telescope rather than with your own eyes, the difference is dramatic. So, when astronomers started to use the telescope, they noticed that the center of our galaxy emitted much more gamma radiation than, for example, its outskirts. To put it simply, something is growing incredibly brightly right in the middle of the Milky Way. But the most perplexing thing is that no one has been able to find a plausible explanation for this phenomenon for almost a decade. Some astronomers suggested that the central region of the Milky Way was glowing with such intensity because the dark matter was getting destroyed there. While no one has ever observed dark matter annihilation, scientists have been hypothesizing about this phenomenon for a long time. Naturally, we wouldn't be able to see dark matter itself, but the process could be producing the radiation the gamma ray telescope has spotted. That's how it could be happening. If particles of dark matter collided, just like ordinary matter particles do in particle accelerators, they would annihilate one another, and as a result, they would burst into a shower of other particles, including the ones that make up gamma rays. But that's where the problem lies. If the mystifying glow was created by the annihilation of dark matter, then gamma ray particles would get distributed evenly in space. Instead, they gather together in clumps. That's why, to the great disappointment of numerous supporters, the theory based on the dark matter came up short. There is an alternative explanation of why the Milky Way is glowing. The culprit might be a group of millisecond pulsars, which are neutron stars spinning incredibly fast. And when I say fast, I mean about 1,000 times per second. The theory that the glow is caused by millisecond pulsars is quite plausible. As I mentioned before, the light coming from there is clumpy rather than smooth, and it often happens when the source of light is one individual object, such as a pulsar. Several studies have concluded that, due to the nature of the light, millisecond pulsars are the best explanation for this phenomenon. However, many scientists are still not persuaded. Those stubborn folk want proof, right? Well, first of all, they state that the clumps of light may appear due to the interaction of gas between stars and cosmic rays. Besides, the pulsar theory has one more catch. Why would so many of them be clustered together in a perfect sphere around the center of the Milky Way? Probably the clusters of stars that orbit the Milky Way could have been disrupted by the galaxy's gravity. As a result, these spilled stars, including pulsars, later formed a spherical shell around the center of the Milky Way. But, in fact, the whole picture looks like something completely different from both pulsars and dark matter. It leaves scientists with more questions than answers, and all that's left to do is a lot more research and testing.